Welcome to our last lesson on trig identities. In this video we'll be looking at the sum to product and the product to sum identities. And just kind of similar to what we've done in the previous lessons, we'll look at first just stating what those identities are, and then just how we recognize them when we see them. And then we'll look through a few examples just to show how we can use these identities to simplify other trig expressions, or to compute the exact values of trig expressions, or to prove some sort of identity. So let's first start with stating our identities, and there's two groups. Each group has four identities that we are going to list out. And the first group is from the product to sum identities, and so we have a multiplication. Product is multiplication. So if we're multiplying a sine or a cosine together, it allows us to convert it from a multiplication, from a product, into a sum, or technically it's a plus or minus, depending on the formula that we have. But let's just run through these real quick. So if we have the product of sine of A times the cosine of B, we can rewrite that as 1/2 times the quantity of the sine of A plus B plus the sine of A minus B. If we flip that around, if we have the cosine of A times the sine of B, we can rewrite that as 1/2 the quantity sine of A plus B minus the sine of A minus B. If we now have two cosines, so the cosine of A times the cosine of B is equal to 1/2 the cosine of A plus B plus the cosine of A minus B. And then we have the sine of A times B, the sine of A times the sine of B is equal to 1/2 times the quantity cosine of A minus B minus the cosine of A plus B. Again, so these are the four identities. It allows us to take a product of two sine or cosine expressions and split them apart into their sum. All right, the other grouping that we have is sum to product. So if we have the sum, so sum is addition, product is multiplication. So if we have the sum, or really the difference, of two sine functions or two cosine functions, then we can rewrite those in terms of their product. So if we have the sine of A plus B, we can rewrite that as 2 times the sine of the quantity A plus B over 2, and then times the cosine of the quantity A minus B over 2. Similarly, if we have sine of A minus the sine of B, we can rewrite it as 2 times the cosine of A plus B over 2 times the sine of A minus B over 2. And then we can do the same thing for cosine. So cosine of A plus the cosine of B is equal to 2 times the cosine of A plus B over 2 times the cosine of A minus B over 2. And then if we have the cosine of A minus the cosine of B, we can rewrite this one. It's a little different, but we have a -2 out front times the sine of A plus B over 2 times the sine of A minus B over 2. So those are the 8 sum to product, product to sum identities. And again, it's just allowing us how either to break a multiplication apart into an addition or subtraction, or how we can combine an addition or subtraction into a product. All right, so let's look through just a few examples here. So this first example, we're given the expression 11 times the sine of x over 2 times the cosine of x over 4. And we want to use our product sum identities to express this product as a sum. So one thing to notice here is that the expression inside the sine and the cosine are not equal to each other. What I mean by that is we have an x over 2 and an x over 4. So these are different expressions. So we're going to have to think of these as the A and the B. When we talked, and the reason I point that out is when we talked about the double angle identities, we had a very similar expression, but it was the sine of theta, cosine of theta. So we talked about, our double angle identity was 2 theta is 2 sine theta times cosine of theta. So had the x over 2 and the x over 4 actually been the same thing, so say they'd both been x over 4, then we actually could have used the double angle identity instead of using a product to sum. You could still do the product to sum, but we could have maybe done a little easier approach and used the double angle identity. But we can't use that here, again, because we have two different expressions. We have an x over 2 versus an x over 4. So we can't use the double angle identity. We have to try something else. And so we know we have a product here, right? Because there's a multiplication here in the middle. So we have, our identity that we're going to use is if we have the sine of A times the cosine of B. Well, what is sine of A times cosine of B? That's a product. And our identity told us that was equal to 1/2 times the quantity of the sine of A plus B plus the sine of A minus B. Okay, so A in this case is the x over 2, B is the x over 4. And then one other little extra part here is we have an 11 out front. So this 11 is being multiplied by the sine of A and the cosine of B, which means if we have an 11 out front for our identity, so it's 11 times the sine of A and the cosine of B, that means we're going to have an 11 times the 1/2 out front, and then the sine of A plus B plus the sine of A minus B. So let's go ahead and rewrite or write out what this would look like. So we have 11 times the sine of x over 2 times the cosine of x over 4, and that will equal an 11 times 1/2 times the quantity of the sine. So for A plus B, it's going to be x over 2 plus x over 4 plus the sine of A minus B, so x over 2 minus x over 4. So to simplify that, we can multiply 11 times 1/2, which the 11 again is just over a 1. So 11 times 1/2 would be 11/2. You could also write that as a decimal. It would be 5.5. So 11/2 times the sine. And in order to combine the x over 2 and the x over 4, we need to write a common denominator, which would be 4. So the x over 2 we could write as 2x over 4. So we have 2x over 4 plus x over 4. And then we have plus the sine of 2x over 4 minus an x over 4. And then one more step, we can actually do that addition and subtraction. So equals 11/2, or 11/2 times the quantity of the sine of 2x plus x, which is going to be 3x over 4, plus the sine, 2x minus an x would just be another x, so x over 4. And we close our brackets there. So we're able to rewrite 11 sine of x over 2 times the cosine of x over 4 as 11/2 the sine of times the quantity sine of 3x over 4 plus the sine of x over 4. All right, let's try another example. This time we're going to try and compute an actual value here. So we are trying to compute the cosine of pi over 12 plus the cosine of 5 pi over 12. Now, there are several ways we could do this. In the previous lessons, we looked at how we could compute just, say, the cosine of 5 pi over 12. And there's actually two ways we could do that. One was using the sum and difference identities. So, for example, we could rewrite 5 pi over 12 as, we could rewrite 5 pi over 12 as 3 pi over 12 plus 2 pi over 12. And so those simplify into unit circle values, and then we can do the whole sum identity. And then we could do a similar thing with a difference for pi over 12. We also looked at how we could think of pi over 12 as a half angle. So we know pi over 12 is the same thing as pi over 6 divided by 2. So it's half of pi over 6. So we could do a half angle identity. I don't really want to do the half angle identity because for cosine you end up getting the square roots and that can be really messy. So I don't really want to do that. It is a good option, it's just not one that I want to do right now. And the other option is the sum and difference, which again we could totally do. We've done examples like that before, but you're going to have to do the sum and difference twice, once for the pi over 12 and once for the 5 pi over 12. So I kind of don't want to do that either. We could, but I just don't want to right now. So instead, is there an identity that we have for the sum of two cosines? Well, yes, there is. We know that the cosine of A plus the cosine of B is equal to what? Cosine of A plus cosine of B is equal to 2 times the cosine of the quantity A plus B over 2 times the cosine of the quantity A minus B over 2. So we're able to take this sum of two cosines and convert it into the product of two cosines. Now, hopefully that's going to help us, but let's see what happens when we do this. So we can take the cosine of pi over 12 plus the cosine of a 5 pi over 12 and rewrite that as 2 times the cosine. So it's a plus b over 2, so it's going to be pi over 12 plus 5 pi over 12 all over 2 times the cosine of pi over 12 minus 5 pi over 12 all over 2 again. Okay, so we've rewritten the sum now as a product. And so all that's left really is just simplifying and then computing the actual value. So we have 2 times the cosine. Now in this example it's nice because both our pi expressions are already in common denominator. So we can just go ahead and add them together. So pi over 12 plus 5 pi over 12 is going to be 6 pi over 12. And we still have that over 2 times the cosine, and pi over 12 minus 5 pi over 12 would be a negative 4 pi over 12. And again, that's still over a 2. So let's simplify those first enumerator fractions. So 2 cosine, so 6 pi over 12, the 6 and the 12 reduce down to just pi over 2. And again, that's over 2 times the cosine of a negative 4 pi over 12 will reduce down to pi over 3. And again, that is over 2. And then let's get rid of the over 2. So let's simplify that. So we have 2 cosine. So pi over 2 divided by 2 becomes pi over 4. And then a negative pi over 3 divided by 2 becomes a negative pi over 6. Okay, so we've simplified this down to really nice expressions here. And one other maybe little step is we have the cosine of a negative pi over 6, and we have an identity that deals with that negative. So we have 2 times the cosine of pi over 4 times the cosine. So if we use our even and odd identity, we know cosine is even. And that means the cosine of a negative theta has to equal the cosine of just the positive theta. So we actually don't need that negative there. We could just rewrite this as the cosine of pi over 6. That just makes it a little easier. We don't have to worry about negatives and all that sort of stuff. It's just easier to compute. So we now have two cosines, and they're reduced down to unit circle values, pi over 4 and pi over 6. So let's actually compute what those are. So we have 2 times, so what's the cosine of pi over 4? Looking at our unit circle, that comes out to be root 2 over 2. And then we have the cosine of pi over 6, which according to our unit circle, that would be root 3 over 2. And so we can multiply those together. We have a 2 times a root 2 and a root 3, which would be a root 6, divided by a 2 times 2, which is 4. Remember the 2 out front, you could think of as having a 1 in the denominator. So we have 2 root 6 over 4, and the 2 and the 4 reduce a little bit, so we end up with a root 6 over 2. So the sum of cosine of pi over 12 plus cosine of 5 pi over 12 will turn out to be a root 6 over 2. And again, we could have gotten the same answer using the other methods. It may have been a lot harder to come up with such a nice answer though. So these identities were really helpful in this case. All right, let's look at one more example. Let's look at how we can use these product to sum identities to verify a trig identity. So remember, when we're doing identities, we're not treating them as an equation, so we're not going to add and subtract something to both sides of the equation. In fact, I often kind of try to draw a line here just to separate it, so you work with one side or the other. You don't use both of them simultaneously. And often it's helpful to start with the side that is more complicated. So we have the quantity, the fraction of the sine of 3x plus the sine of 7x divided by the cosine of 3x minus the cosine of 7x. And we know we want to show that that is equal to just the cotangent of 2x. Okay, so definitely the left side of this equation, the left side of this identity, is the most complicated, right? We have the sine of 3x plus the sine of 7x divided by the cosine of 3x minus the cosine of 7x. So that's definitely the most complicated side, so hopefully we can do something to simplify it. Again, remember our end goal is to convert it to a cotangent of 2x. So as we look at this, we have in the numerator, we have the sum of two sines. And in the denominator, we have basically the difference of two sines, or two cosines. So we have the two sums here. And so we want to think about what our identities are. So in the numerator, again, we have the sine of A plus the sine of B. And in the denominator, we have the cosine of A minus the cosine of B. Okay, so it's just the sum of two the sum of two sines divided by the difference of two cosines, right? So using our identities, we know the sum of the two cosines, so sine of A plus the sine of B, is 2 times the sine of A plus B over 2 times the cosine of A minus B over 2. And for the cosines, we know that the cosine of A minus the cosine of B we could rewrite as a negative 2 times the sine of A plus B over 2 times the sine of A minus B over 2. Okay, so we're just going to use those two identities. So let's start with the sine of 3x plus the sine of 7x. In this case, the 3x is our A and the 7x is our B. So we could rewrite the sine of 3x plus 7x as 2 times the sine of 3x plus 7x all over 2 times the cosine of 3x minus 7x all over 2. And that would be divided by a negative 2. So we're going to do the cosines now. Cosine of A minus B turns out to be negative 2 times the sine of 3x plus 7x over 2 times the sine of 3x minus 7x over 2. All right, so let's simplify our fractions a little bit. So we're going to have a 2 times the sine, so 3x plus 7x would be a 10x over 2, and then we'd have the cosine of 3x minus 7x, which would be a negative 4x over 2. And then all of this is going to be divided by a negative 2 times the sine of 10x over 2 times the sine of a negative 4x over 2. Now, one thing we can actually do right now is both in the numerator and the denominator we have a 2, so we can cancel the 2 out. We still have that negative in the denominator, but we can cancel the 2's out. And also notice in the numerator we have a sine of 10x over 2, but we have the same thing, sine of 10x over 2, in the denominator. So those are actually going to cancel out. So that really simplifies, clears out a lot of the stuff that we have in this problem. So all we're left with is a cosine in the numerator and then a sine in the denominator with a negative out front. So let's simplify some of this a little bit. We have the cosine of a negative 4x over 2. That would become the cosine of a negative 2x, because the 4 divided by 2. And in the denominator, we're going to have the negative sine of also a negative 2x. Okay. So let's now apply the even and odd identities. We know cosine is even, so that means for cosine we can just get rid of that negative. So it's become the cosine of a positive 2x. And in the denominator, we already have a negative out front, but I have a negative inside the 2x with the 2x. So I'm going to take the negative in there with the 2x and pull it out front. So we're actually going to have a double negative out front here. So it's the negative of a negative sine of a positive 2x, which those double negatives are going to cancel out and leave us with the cosine of 2x over the positive sine of a positive 2x. And we know that cosine over sine is cotangent, so this turns out to be the cotangent of 2x, and that is what we were trying to show to begin with. That's what the right side of our identity was. So we were able to use our sum to product identities. We used 2 of them, and then we reduced some stuff and used our even odd identities to show that the sine of 3x plus 7x divided by the cosine of 3x minus the cosine of 7x is actually equal to the cotangent of 2x.